So we're going to solve some Kirchoff's laws problems. And you'll see here I've just written a problem that I happen to find in one of the textbooks. And for the moment, I just want you to look at the blue. So we've got a circuit here. We're looking for I1 and I2, and we're looking for this EMF over here, and we know what this ammeter reads. Now, the first thing that we have to do is decide how we're going to walk through the loop. Now, you can just guess which direction you can walk through the loop in. Personally, I prefer to just walk with the direction of the current. So this 5 volt battery here, we know the current's going to be flowing this way, and we're going to just assume, or I'm going to just assume, that we're going to walk through this way, and the current's going to be flowing down that circuit in that direction too. Okay, so I'm going to assume current, I1 comes into this node, this one here, I3 comes out of that node. Okay, if you guess wrong, that's fine. You'll just end up with a negative number when you get to that point. So let's look at our first one, our green one. We're first looking for that I1 current. So it's always a good idea to write our loop law here. The sum of the voltages around a loop equals 0, and draw the direction of your loop on your diagram. I suggest you take a couple of different colors of pen, not red, so that you can make it really clear to your examiner what you're doing. So let's start here with our battery, and we can say, well, we are going to add 5 volts. We are walking through that battery in the direction of the current. We have added 5 volts to our loop. As we go around, okay, we get to here and we're like, oh, we're still walking in the same direction as the current, which means this resistor is using up voltage. So that's where our minus sign comes from. And the stuff in the brackets is Ohm's law, V equals IR. Okay, so the voltage drop across this resistor is going to be I, which we know is 0.75 from the instructions, and R, 4 ohms. So we keep walking around, we get to here and we're like, oh, still going in the same direction, so it's going to be a minus, and we're going to use Ohm's law again. We know that this resistor, the 2 ohm resistor, will have I1 flowing through it, which means the voltage drop across it must be 2, the resistance, times I1. And so you can see here, I've written a really simple mathematical expression for that. 5 volts goes in, however much this is gets chewed up by the 4 ohm resistor, and however much this is gets chewed up by the 2 ohm resistor. And we can use this to solve for I1, and it turns out I1 is 1 amp. Okay, at that point there, we're like, well, how are we going to find I2? And the answer is we're going to use Kirchoff's current law. And I've written that down too. I prefer to write Kirchoff's current law this way, that the sum of the currents at a point is equal to 0, but you will often see it written, in this case, you'll see it written I1 equals I2 plus I3. So the current coming in equals the 2 currents coming out. And that's fine if you prefer to write it that way. And you'll see I've labeled point A, and down here I've written it. So it's nice and easy to see. And so when we say that, we say I1, we know that, we just worked it out, 1 amp minus 0.75, that's the current flowing down this way, coming out of it, plus I2, because we don't know yet what that is, and it works out that it's 0.25 amps. And that makes sense. 1 minus 0.75 equals 0.25. And the last bit we do is we work out loop 2. And we work out loop 2 to give us that other EMF. And we say the sum of the voltages is equal to 0. Now, I hope you've got it fixed in your head how it looks, but we write our loop law again. We've got our EMF, and we say, well, because we're walking in the same direction as the voltage, our EMF is going to be positive. We're still walking through our loop in the same direction as the current when we get to this 4 ohm resistor, so it's going to be a minus. Okay, so minus 0.75 times 4, that's Ohm's law there. But this next one's going to be a plus, because this time we're walking against the current flow for this one here. Okay, and that's why we get 0.25 times 8, I3 times the 8 ohm resistor. And that works out to give us a 1 volt EMF on that battery there. Now, let's take a look at this one here. And this one here we've labelled A, B, C, D, E, and F. Okay, and we've got our we've got two batteries, we've got some currents flowing, and we've got a bulb of some kind. Okay, and often you'll see in exams and things, you'll write an expression for the resistance, the current through its bulb R, and show its direction on the diagram. Okay, so I always like to write Kirchoff's point law or loop law at this point. And since I'm looking for IR, I'm going to assume that this is going to be a point law example. Sum of the currents equals 0 at a point, and in my case, it's point F. So I write this, either I1 plus I2 plus I3 equals 0, or in our case, we're saying, well, here's the current flowing here, here's the current flowing in there. I3 must be flowing out. You can see I've drawn it on with a green arrow. I3 equals I1 plus I2. So now it says write an equation for all the potential differences around the top loop, and they've helpfully given it us. You go from B, A, F, C, and back to B, and solve it to find the relationship between I1 and I2. This means we're not actually solving to get a number value, we're just solving to get the ratio. And this is important because this sort of simultaneous equation turns up in Kirchoff's loop laws problems all the time. So we're just doing Kirchoff's loop law here, okay, and I've started at point B. Okay, if we look at this diagram again, you'll see I've drawn it on. I'm starting at point B. I'm going to go through the resistor, then I'm going to go through the battery, then I'm going to go through the other battery, then I'm going to go through the other resistor till I get back to there. Okay, so here's our current, and it's a minus because I'm walking through that resistor in the same direction as the current. So it's minus 2I1 plus 1.5 because I'm going through that battery in the same direction as the current, minus 1.5 because I'm going through this battery in the opposite direction to the current, plus 1 times I2 because I'm going through this resistor in the opposite direction to the current. And what we can find out eventually is that I2 equals 2 times I1. Okay, we've got a ratio between those two things now. If I1 equals 0.3 amps, what will the voltage over branch AB be? Okay, this took me a little bit of time to kind of figure out what they were asking for because that's not necessarily very easy to see. But basically what they're saying is the voltage is basically the loop law on a tiny part of the loop. And so across branch AB, we've got a battery putting voltage in, and we've got a current, a resistor eating voltage up. So 1.5 minus the voltage drop across that 2 ohm resistor. And it works out that that comes out to 0.9 volts. Okay, 1.5, the stuff put in by the battery, minus 2 times 0.3. Now we're going to find the resistance R of the light bulb. And this might look like it's really easy, but it's a two-step problem. First, we're going to apply Kirchoff's current law. We're going to say, well, the resistance of the light bulb, the current flowing through the light bulb, is equal to the two currents flowing in. And when we add them together, we can say, well, at this point you might get a bit disheartened, but we have an expression for I2. We know that if I1 equals 0.3, I2 must equal twice as much. And so it works out that the current is 0.9 overall. And then we use Ohm's law, R equals V over I, and it works out that that resistance must be 1 ohm. That lamp must have a resistance of 1 ohm.